this lesson, we will be solving absolute value equations and inequalities. Our one objective is to solve absolute value equations and inequalities. We've already solved absolute value equations, but I think it's a good idea to review how to do it before we move on to solving absolute value inequalities. Our steps for solving absolute value equations. Number 1, isolate the absolute value. Number 2, write two equations, one positive and one negative. And step 3, solve each equation independently. So our first example is to solve and graph the equation 2 times the absolute value of 3x minus 1 plus 4 equals 20. Our first step is to isolate the absolute value. So the first thing we need to do is subtract 4 from both sides. That will leave us with 2 times the absolute value of 3x minus 1 equals 16. Our next step is to divide both sides by 2. When we do that, we get the absolute value of 3x minus 1 equals 8. Now that we have the absolute value isolated is when we write our two equations. So our first equation is the positive one, 3x minus 1 equals 8. Our second equation is 3x minus 1 equals negative 8. So we'll add 1 to both sides. So now we have 3x equals 9. Dividing by 3, we get x equals 3 for our first solution. Our second solution, if we add 1, we get 3x equals negative 7. Divide by 3. So x is negative 7 thirds. So writing this in set notation, x equals, the smallest answer is negative 7 thirds, and the largest answer is 3. So when we graph these, we graph them as 2 points. So we start at 0, 1, 2, 3, 4. So there's 3, so there's our first point. Negative 7 thirds, 7 divided by 3 is 2 with a remainder of 1, so it's negative 2 and 1/3. 1, 2, 3, so there would be negative 3. Negative 2 would be here, so right about here would be negative 7 thirds. Please take a minute and try this example on your own. After you've completed it, restart the video and watch how it's done to make sure you solved it correctly. Our first step in solving this equation is adding 6 to both sides. When I add 6 to both sides, I'm left with negative 2 times this absolute value of x plus 1 equals negative 34. My next step is to divide by negative 2. Once I've done this, I have the absolute value of x plus 1 is equal to 17. Now that the absolute value is isolated, I can write my two equations. My first equation is x plus 1 equals 17. My second equation would be x plus 1 equals negative 17. To finish solving, I subtract 1 from each equation, so the first answer would be x equals 16. Subtracting 1 over here, my second answer is x equals negative 18. And now I graph them on the number line. I'm going to use a scale of 2. So there's 0, 2, 4, 6, 8, 10, 12, 14, 16, 18. So right there would be negative 18. So I put a point on negative 18. And then 2, 4, 6, 8, 10, 12, 14, 16. There's 16. And I put a point on 16. So our two solutions are x equals negative 18 and 16. So moving on, a little review on extraneous solutions. An extraneous solution is a solution of an equation derived from an original equation that is not a solution to the original. Sometimes extraneous solutions happen when we have an x inside the absolute value and another x outside the absolute value. In this case, the absolute value is already isolated, so I can go straight to setting up my two equations. So my first equation would be 3x minus 4 equals negative 4x minus 1. For my second equation, I would multiply one side or the other of this by negative 1. In doing so, I get 3x minus 4 equals positive 4x plus 1. So now we'll go through and solve our equation. I need to put the x's on one side, so I'm going to add 4x to both sides. So 3 plus 4 would give me 7x minus 4 equals negative 1. I can add 4, so 7x equals 3. Divide both sides by 7, so x is 3/7. For the second equation, I'm going to subtract 3x from both sides. So I get negative 4 equals x plus 1, subtract 1. So I get x equals negative 5. Now this is the important part because I have to substitute back into the original equation to check. So I have 3 times 3/7 minus 4 should equal negative 4 times 3/7 minus 1. So 3 times 3 would give me 9/7 minus, I'm going to get a common denominator, so that would be 28/7. Now remember, this side of the equation was originally inside absolute values, so this needs to be contained inside absolute values. So that should equal, on the other side, I have negative 12/7. Getting a common denominator, I'm going to have negative 7/7. Now, at this point, there's no reason to continue checking because I have an absolute value on the left-hand side, which is always going to be positive. And on the right-hand side, I'm going to have a negative number, so that's not going to work. So that answer, the 3/7, is extraneous. So now I'm going to move on and check the negative 5. The absolute value of 3 times negative 5 minus 4 should equal negative 4 times negative 5 minus 1. So the absolute value of negative 15 minus 4 equals negative 4 times 5 would be positive 20 minus 1. Negative 15 minus 4 would be negative 19 equals 19. And the absolute value of negative 19 is 19. So therefore, this is the solution that works. 19 equals 19. So when I graph my solution, the only one I graph is the negative 5. So I put a point at negative 5 on my number line. Extraneous solutions happen, remember, when we have one x outside the absolute value and another x inside the absolute value. So when you see this at the start of the problem, make sure when you find your two solutions, you check both of them to see which one, if either or both, happen to work. Next, we're going to talk about solving absolute value inequalities. And the first type we're going to talk about is the absolute value of A is greater than B. So when we think about graphing the absolute value of x is greater than 4, so I'm going to start with a number line, 0, and I'm going to go by 2s. 2, 4, 6, negative 2, negative 4, negative 6. So absolute value means the distance from 0. So we're looking for numbers where the distance from 0 is greater than 4. So 6, that's more than 4 units away. 5 would be more than 4 units away. 4.01 would be more than 4 units away, but it's so close to 4 that I can't actually put a point there. So I'm going to put an open circle to show that I'm going to get really close to 4, but not actually touch it. And if I get thinking about it, all these other decimals are also going to work. Now, because distance can go in both directions, I'm going to have the same thing over here on the negative side. So, when we have a greater than, they're solved as or compound inequalities. We learned about compound inequalities in our last lesson, and we learned that it's okay if compound inequalities, if they're an or, go in different directions, because the solution only needs to fit one or the other part. So, if we have greater than or equal to, they're solved as or inequalities, because those ones are greater than our solution, so they're going to be graphed outside. So when we isolate the absolute value, then we write two inequalities, one positive and one negative. Now, when we do the negative inequality, we're technically multiplying by -1. Whenever we multiply by a negative, we have to reverse the inequality symbol, and it's no different here. So when we write our two inequalities, we have to reverse the sign for the -1, and then we solve each inequality independently and graph. So the first example, the absolute value of 2x minus 5 is greater than 3. Our first inequality would be 2x minus 5 is greater than 3. The second one would be 2x minus 5 is less than -3. Now we solve, so I'm going to add 5 to both sides. So I get 2x is greater than 8, divide by 2, so x is greater than 4. For the second one, if I add 5, I get 2x is less than 2, divide by 2, so x is less than 1. To write this solution, we write x is less than 1 or x is greater than 4. And then we graph it. So I have to go greater than 4, less than 1, so I'll start at 0. 1, 2, 3, 4, 5, and I've got space, so I may as well go to 6 and 7. So there's 4, 1, 2, 3. So it's strictly less than, so it's an open circle at 1, and then everything to the left of 1, everything less than 1, or x is greater than 4. So start at 4 and go to the right. If we're graphing a less than inequality, if we want to graph the absolute value of x is less than 4, so on my number line, I'll once again go by 2's. So now I want all the distances that are less than 4 away from 0. So I'll have an open circle at -4 because I can get really close to it but can't actually touch it. The same thing will happen at 4, but this time I want everything that's closer than 4 units to 0. So it's everything in between the two circles, which means that less than or equal to inequalities are solved as and compound inequalities, which means that the only solutions are the solutions that make both pieces of the inequality true. So let's take a look at this example. My first step, I'm going to subtract 5 from both sides because I have to isolate the absolute value. So I get -2 times the absolute value of x plus 1 is greater than or equal to -8. Now, to continue isolating the absolute value, I have to divide both sides by -2. In doing so, I get the absolute value of x plus 1 is less than or equal to, I divided by a negative, so I have to reverse the sign, 4. Now I write my two inequalities. X plus 1 is less than or equal to 4. I also get x plus 1 is greater than or equal to -4. So if I subtract 1, I get x is less than or equal to 3. If I subtract 1, I get x is greater than or equal to -5. So I want all numbers that are less than 3 and greater than -5. So I can put the word and in between here, and that's one way to write the answer. The other way to write the answer is I can start with -5 is less than or equal to x, which is less than or equal to 3. And now I've written it as one single statement rather than having to use the word and. And it's clear that x is going to be between 3 and -5. So when we graph this on our number line, 0, 1, 2, 3, this time because our endpoints are included, I'm going to use closed circles, 1, 2, 3, 4, 5, and I'm going to shade everything in between those 2 points because our solution is everything closer. Now we're going to work on some real-world examples. Many times when you're manufacturing things, you can't get exactly the amount that you want. So what happens is manufacturers set up tolerances for what they're making. A tolerance means that what we're doing has to be within a certain range in order to be approved and then sold and distributed. So in this case, our example says a manufacturer has a 6/10 ounce tolerance for a bottle of salad dressing advertised as 16 ounces. Write and solve an absolute value inequality that describes the acceptable volumes for the 16-ounce bottles. So in order to do this, there's a little equation that helps us. Actually, it's not an equation, it's an inequality. So it's x minus the actual, or instead of actual, you can call it the desired. Okay. So it's the absolute value of x minus the actual, or x minus the desired, has to be less than or equal to the tolerance. So if we use this to help us, our actual or desired is 16 ounces, and that has to be less than or equal to the tolerance of 6/10 of an ounce. So when we set up and solve this, we get x minus 16. We don't need the absolute value anymore because we're setting up our two equations. So we have x minus 16 is less than or equal to 6/10. And then we have x minus 16 is greater than or equal to negative 6/10. So when I add 16, I get x is less than or equal to 16 and 6/10. When I add 16 over here, I get x is greater than or equal to negative 6/10 plus 16 would be 15 and 4/10. So write and solve an absolute value inequality that describes the acceptable volumes. So the acceptable volumes are in the range, and then we can write this as a compound inequality. 15.4 is less than or equal to x, which is less than or equal to 16.6. Example 7, a city ordinance states that pools must be enclosed by a fence that is from 3 feet to 6 feet high. Write an absolute value inequality describing fences that do not meet this ordinance. So if we think about this in terms of a number line, 1, 2, 3, 4, 5, 6. So the fence has to be between 3 feet and 6 feet high. So that would be everything in here. However, we want the ones that do not meet this ordinance. So to not meet this ordinance, we're going greater than or less than. So an absolute value inequality that would be outside of this region. So in order to go outside, we have to first be able to figure out what our midpoint here is. So if we do 3 plus 6 divided by 2, that would be 9 over 2. And since we're talking about fence heights, this is one where it probably makes sense to say 4.5. So the absolute value of x minus the desired, so 4.5. Now, because we're going fences that do not meet this ordinance, we're going to say they're greater than or equal to. Now, 4.5 would be right here. So to get to numbers that are outside of that, we have 1.5 units. Now, if we think about this, the fence is from 3 feet to 6 feet high. So if I have a fence that's exactly 3 feet, I'll meet the ordinance. So I don't want the equals sign this time. I want to get rid of that and just have x minus 4.5 and take the absolute value of that is greater than 1.5. And that is the absolute value inequality that describes fences that do not meet the ordinance. Throughout this lesson, we started with a review of solving absolute value equations, where we made 2 equations, solved each equation, wrote our answer in set notation, and then graphed them as points on a number line. We then discussed extraneous solutions, solutions that look like they answer the problem, but when we check them, we determine that they are not actually solutions to the original equation. We then went on to solve absolute value inequalities. We learned that greater than absolute value inequalities are solved as or compound inequalities. And we learned that less than absolute value inequalities are solved as and compound inequalities. We also discussed word problems, and we have a little formula to help us when we have to do absolute value inequalities, x minus the actual or desired, and it's the absolute value of that, is going to be less than or equal to the tolerance, so the amount that we're allowed to vary by. Another word for tolerance that you will see sometimes is variance. So either one of those words, tolerance, variance, that's how much our actual or desired amount can vary by and still be accepted. And then for our last equation, we wanted fences that did not meet this ordinance. So the first thing we had to do was we had to figure out what the perfect fence would be. So 4.5 feet would be right in the middle, so that would be our desired amount. Then from there, fences that do not meet this ordinance would be more than 1.5 feet higher or lower than that midpoint. So that's why our equation is the absolute value of x minus 4.5 is greater than 1.5.